In this part of the lecture, we'll discuss the stability of GRNNs. In particular, we show that as GRNNs can be seen as a time extension of traditional GNNs, they inherit their stability properties. We'll start by recalling the notion of relative perturbations modulo permutation discussed in previous lectures. For two graph shift operators S and S tilde, we define the set of perturbation matrices modulo permutation as the set of matrices E that satisfy the expression indicated in equation 1, where calligraphic P is the set of all permutation matrices. We measured the distance between S and S tilde as the minimum of the norm of the matrices E that relate S and S tilde in the set calligraphic E. Then, if S tilde is a permutation of the shift matrix S, their distance equals 0. Now, we recall the definition of integral Lipschitz filters. We say that a filter A of S is integral Lipschitz if there exists a positive constant such that the spectral representation A of lambda satisfies the condition indicated in 2. Notice that integral Lipschitz filters also satisfy that the absolute value of lambda times the derivative of A of lambda is bounded by a constant. This implies that the frequency response of the filter becomes flat for large values of lambda. We consider a GRNN with one input feature, one state feature, and one output feature, described by zt and y hat t as indicated. Additionally, we consider the following assumptions. The filters A, B, and C are Lipschitz integral with constants Ca, Cb, and Cc, and whose norm is unitary. The nonlinear functions sigma and rho are Lipschitz with Lipschitz constant equal to 1, and they have 0 as a fixed point. The initial hidden state is identically 0. This means Z0 is equal to 0. Additionally, the norm of xt is lower or equal than the norm of x for all t. Now we formally present the stability theorem for GRNNs. Let S and S tilde be the graph shift operators of the graph and of the perturbed graph. And let E be a matrix in the set of relative permutation perturbation matrices such that the distance between S and S tilde is lower or equal than epsilon. Let YT and Y tilde T be the outputs of the GRNNs running on S and S tilde respectively. Satisfying assumptions A1 through A3, we have that the minimum norm between YT and the permuted version of Y tilde T is bounded as indicated in 3, where capital C is the maximum of the Lipschitz constants and delta indicates the difference between the eigenvectors of S and E. We have that GRNNs are stable to relative perturbations with a constant that depends on C, N, delta, and T, the process length. Notice that C could be set at a fixed value or it could be learned from the data through the filters A, B, and C. That is, it is a design parameter. Also notice that the term 1 plus delta times square root of n is a property of the graph perturbation and it cannot be controlled by design. The eigenvector misalignment delta measures the degree of commutativity of the product of the matrices S and E. It is also worth noting that the stability bound depends on the polynomial form from T, which is due to the recurrence relationship in the computation of Zt.